Oh, thank you. I'm grateful that I can talk after Yuan because I'm going to talk about eigenvalue transformation. So these are my collaborators. The original plan is to talk about this paper, as the long title indicated. But in the past few months, we made some unexpected progress, and which achieves a near optimal dependence on all parameters. So the talk really squished those two things together. Okay, I'm gonna tell you what is LCHS and why is eigenvalue transformation. We want to solve this time-dependent linear differential equations. If A doesn't depend on t, then this is really e to the minus at, which is an eigenvalue transformation you have seen before. But at in general is time-dependent matrix. You need to do something more. If at is I times the Hermitian matrix, this is called a Hamiltonian simulation. For general at, the propagator is a time-ordered integral. And if A is time independent, this is just e to the minus at. There are some applications, classical linear ODEs and many PDEs, some imaginary time quantum evolution, aka Gibbs state preparation, a way of doing that, and some non-Hermitian quantum physics. As far as I know, it is still open question whether end-to-end quantum advantage can be achieved for any of these applications. This talk doesn't address that. It's really, given this problem, how to solve it. You can also generalize it a little bit to the inhomogeneous case, which means that there is a plus BT. Then you can just do apply this method and apply the so-called Duhamel's principle, aka variation of constants, and so the same thing. Setup is that you want to solve this equation. We're going to do something called the Cartesian decomposition of AT, which means that A, for any matrix A, whether it's diagonalizable, so on and so forth, it doesn't matter. You always compute the so-called matrix real part, that is A plus A Hermitian conjugate divided by 2, called L. And then this is the so-called imaginary part. Then any matrix, you can do this. So both H and L, they are Hermitian matrices. We further assume that L is positive semi-definite for stability reasons. We assume that we can query L and H. The main result for the LCHS is that you give me this A, I have access to the L and H. L is positive semi-definite for all the t. Then the following identity holds, which means that the time-ordered propagator is given by this integral linear combination in the sense of a continuous thing, 1 over 1 plus k squared, a known kernel, times ukt, where uk, they are propagators corresponding to a Hamiltonian simulation. It's a little bit weird Hamiltonian simulation because it's not like some A, because A can be even, non-diagonalizable, so on and so forth. Doesn't need to be normal matrices, really anything. Then this Hamiltonian depends on K. K is a scalar. KL plus H. Okay, why is like that? But this is a matrix identity. Let's try to understand where this comes from some special cases. The special case 1 is A only involves the H, which is there's only anti-Hermitian part. Then you plug this in, you realize that it doesn't even depend on K, so you just pull it out. You realize I'm saying nothing, but this is a probability density. Indeed, this is called the Cauchy probability density, which is completely trivial. Slightly not trivial is that when A is just L, then what I'm saying is really this guy is the Fourier transform. The Fourier transform of this is e to the minus x absolute value. That is why I need L to be positive semi-definite. And then you plug in the spectral mapping theorem as you have seen before, and you can prove it. The tricky thing is when A involves both L and H, then this one doesn't fall into any of the category. And indeed, this is generically eigenvalue transformation problem rather than single value transformation problem. Furthermore, L and H, they do not commute. Nonetheless, this identity still holds. Let's first assume this works. If there's time, I'm gonna briefly say where it comes from. We have this LCHS identity. We can implement efficient quantum algorithm. what we do is that you truncate this integral to some finite range. The range needs to be chosen to be 1 over epsilon. The reason is the kernel decays a little bit slowly. It's a 1 over k squared. And then you have many ways to implement it. You can choose to implement this as a linear combination of unitaries, LCU procedure. That is like the fully quantum way of implementing it. Or you can implement it like in a hybrid quantum classical way via importance sampling. And both ideas have been used extensively in the previous works. Just to show you how it works, the LCU is the simplest example is to implement 1/2 U0 plus U1, and this is the circuit. More generally, if you want to implement a linear combination of unitaries in this way, then you need a so-called prepare oracle and a select oracle, and you just compute. You'll realize that if you mirror this and obtain 0, you can have a block encoding of the linear combination of unitaries. That, as I said, is when you have abundant quantum resources and can implement this. Or if you just want to implement the bare minimum, that is, I want to have a quantum circuit that implements the controlled Hamiltonian evolution for a given k, you can actually just use one ancillary qubit, use a Hadamard test-like circuit to just measure some overlap information. That is, you use the weight here, that is completely new, to do importance sampling, and this is just some thing can be done with the swap test, and you can use the Hadamard test circuit to accumulate O1, O2, O3, and you add them all together. This gives you observable related to the final state you're interested in. So Yuan has shown that the quantum eigenvalue transformation is genuinely different from quantum singular value transformation. Here, let's consider the problem of solving time-independent differential equation. And the QSVT is applicable when A is Hermitian or anti-Hermitian, when it is normal, but not neither Hermitian or anti-Hermitian. You already need to work quite a bit. And here the LCHS is applicable to the case where A is not even normal, but we do need to add this condition that L is a positive semi-definite. It is equally applicable when A is just a time-dependent thing and the identity still holds. So we have heard from the previous talk that there's a completely different way of doing eigenvalue transformation. So in terms of quantum algorithms, we might be at a very interesting point that a unified theory for eigenvalue transformation is still hasn't emerged yet. So what are the previous works for solving general time-dependent linear differential equations? Most of this is Dominic Berry proposed the first method and proposed the idea of converting the linear differential equation problem into linear system solving problems. And most of the methods in the field, for example, these ones, they're all within the same category, but there's more and more improvements. And we propose some different methods, and the LCHS is actually closest related to the so-called Schrodingerization approach. If you're new to the field, I actually quite recommend you for Defang's tutorial talk on quantum algorithms for dynamic simulation is available online and could be useful. So how is this different from the linear system approach? First, I want to say that Hamiltonian simulation is really something that's rather special because you have some tool called oblivious amplitude amplification. You just do a time marching and then you can propagate it from time from t equals 0 to time t. In general, you couldn't do that. You discretize the system, the differential equation. For example, using the simplest discretization, you can definitely do better than that. You have a gigantic linear system and called the history state, we have seen from the previous talk. And then you apply HHL algorithm or more advanced linear system solvers to solve this very big linear system. And the problem of this, I mean, first, the good things about that is the most advanced version by Barry da Costa last year, 2022, is it achieves very good time complexity, query complexity with respect to the matrix A. here is some block encoding factor. It is linear in simulation time. And Q is some amplification factor that you can do nothing about. That's the nature of the problem. However, because you use linear system solver, the number of queries to the initial state actually you cannot be too low. Especially the number of queries to the initial state depends on t. And in fact, Rolando Soma has some lower bounds showing that in general you cannot expect to do much better than that. LCHS, on the other hand, achieves the optimal state preparation cost. It's just OQ, this physical factor. There's nothing else. However, it's a first order method. The number of queries to A scales like 1 over epsilon. So that's the disadvantage of the method. So as I said, the main drawback is that it's a first order method. For a long time, we thought that's it. The unexpected thing is we just change the method a little bit. Instead of using this kernel, we use this kernel. I'm going to tell you what FK is. Then you achieve near optimal complexity. Boom. So that's the second part of the talk. What we're going to do is to prove this identity. That is e to the minus at. There's also a time-dependent version of that as well. The proof doesn't change. Let's just consider the time-independent version. E to the minus L plus IHT equal to something like this, linear combination of a Hamiltonian simulation. Let's consider the scalar case, although we don't use spectral mapping theorem to prove this. Let's consider the scalar case, that is e to the minus x for x is bigger than 0. Turns out there's a family, there's infinite number of ways of expressing this e to the minus x. And they're all exactly the same, the positive real axis. Here's the example. I'm choosing a bunch of different functions. I haven't told you what is beta yet. They're all exactly the same, e to the minus x on the right half of the real axis. On the left, they all look different. Okay, so this is and we're going to pick the best among them. So this gives you you use the. In other words, you're using some flexibility on the negative real axis to tune the best kernel that gives you the best query complexity. This is the more full version of what we prove. That is for the following identitals. If f is a function that satisfies 3 very mild conditions, one is f is a complex analytic in the lower half plane. 2 is there's a little bit of decay. Any polynomial decay would be fine. And 3 is the whole thing needs to be normalized because you plug in the Hamiltonian simulation, it should just return you 1. And that's it. Then you pick any of this f that works. In particular, the original LCHS just means you pick fz equals to this function. So this is complex analytic in the lower half plane, and it's normalized, and also decays like 1 over z, and therefore it works. Turns out the near optimal method to choose is this weird thing. So e to the 1 plus iz to the power beta, where beta is something between 0 and 1. Immediately you will see that asymptotically on the real axis, that depends on, that determines how far you should go to truncate your integral to obtain a quadrature formula. This thing goes like e to the minus c z to the beta. Beta can be arbitrarily close to 1. So if beta is equal to 1, then this is exponential decay. You just obtain optimal complexity, period. However, we also proved that this is not possible. This is the best thing you can do in the sense that we proved the no-go theorem. That is, if you, within this framework, you choose fk that satisfy all the 3 conditions I described, and asymptotically decays exponentially, literally exponentially, then we prove this is 0. So within this framework, this is the best you can do. So now you can compare with the state-of-the-art methods for solving linear differential equations. You have seen the truncated Dyson method. So it is great in terms of query complexity with respect to time, A, and it's linear in T, log 1 over epsilon square, but it is not good with respect to the initial state preparation. Time marching is our method. It has some near optimal state preparation cost, but here it is quadratic in T, and there's no lower bound has been proven, but we think that you need some fundamentally different idea to remove that t square. The original LCHS, that one is order 1 over epsilon, and the new method scales like almost optimal, and it's a 1 plus 1. The log factor is 1 plus beta inverse, and beta can be arbitrarily close to 1. And then, indeed, this achieves for the first time near optimal state preparation cost and initial state preparation cost at the same time. Let me maybe very briefly talk about some of the proof that is involved. So we couldn't use the spectral mapping theorem because L and H, they don't necessarily commute with each other. What should you do? So the idea is very simple. It's very brute force. And the left-hand side, let's just prove the case for the time-independent case. For the time-dependent case, it's very similar. So on the left-hand side is this e to the minus at. On the right-hand side is this guy. If I want to, I already know at t equals 0, and this is identity, right-hand side is identity. That's the normalization condition. So if I want to prove left-hand side is equal to the right-hand side for all t, I take the derivative and show that the derivative matches at all t. The left-hand side is extremely easy, which is this. The right-hand side is a bit trickier because you take the derivative down and one of the minus ik, one minus ik gets canceled, but then you have this part where this is the Cauchy principal value. So you can see that the structure is that if you can prove this remainder term is 0, then you're done. And what we prove is exactly that. So it's not applying the spectral mapping theorem, but really to show, use the Cauchy's integral theorem, showing that for a matrix valued thing, that is just 0. Okay. So I don't think I have time to talk about that, but it's very, very similar to so-called like Jordan's lemma that you learn at, say, in undergrad complex analysis. So there's this type of contour, and you prove something is converging to 0. What about optimality? So the optimality, what we proved is the following theorem. That is, if f is the function I said like before, it's bounded, and it satisfies exponential decay along the real axis, then you prove this is 0. And the technique of this is kind of interesting. It's called the Fragment-Lindelof principle. It's a generalization of the so-called maximum modulus principle in complex analysis. Again, I don't think I have time to talk about that, and if you're interested, you can refer to the paper. Let me summarize. I hope I've convinced you that for not any linear satisfying the real part needs to be positive semi-definite, which can always be satisfied for finite dimensional matrices up to a shift. Then you can represent that as a linear combination of unitary problems. So it can be solved either quantumly or in a hybrid quantum hybrid fashion with one ancilla qubit. And it is near optimal for pretty general linear ODEs. And there's a further complexity improvement I didn't talk about for time-independent problems, and also Gibbs state preparation over earlier works using similar oracles. So there's some direct extension and future work. So first is can you achieve even better complexity? We're not quite sure, but definitely better time-dependent Hamiltonian simulation and better numerical quadrature techniques could possibly allow us to further reduce the complexity with respect to the polylogarithmic factor. Whether this will lead to other nonlinear, non-unitary dynamics, or let's say general matrix functions, we don't know. As I said, I think we're at a very interesting time right now in terms of developing the unifying quantum algorithms for eigenvalue transformations. Also, we have heard from the previous talk that they were discussing a lot of discussion about the application range of the eigenvalue transformation. Here we require L to be positive semi-definite. That is actually a little bit stronger version of the stability. It's not like any of the stability conditions, they necessarily include one another. but our version is indeed on the stronger side. Whether you can relax that to say only the real part of the eigenvalue of A is on the left half plane, that is an open question within the framework of linear combination of Hamiltonian simulation. Thank you very much for your attention.
Time for questions. Yes.
Thanks for the talk. I have a question. So if you have any extra information about H or L, like their eigenvectors or eigenvalues, could you get better performance through some sort of fast forwarding?
Excellent question. So indeed, in the first work, what we show is that with the application called the complex absorbing potential that is used in chemistry and physics, the L part is just a diagonal, it's diagonal potential. And then you can use interaction picture Hamiltonian simulation, and therefore that application, you achieve near optimal complexity for A and U0 automatically. But the new work shows that you don't even need fast forwarding. You still get near optimal complexity.
So you have a table where you compare the complexity of your approach with previous differential equation solver. Yeah. Can you comment a little bit about, you have this O tilde symbol. Can you comment a little bit about which factors are you hiding with this O tilde symbol?
So the factor, I think there might be some log 1 over epsilon, and there's some, maybe there's a log t. I didn't think about that. So maybe there's some log, I think mainly log 1 over epsilon.
I see. So the t dependence is actually strictly linear with your algorithm, or?
I need to check.
Okay, yeah, thanks.
Any further questions? Yes.
Where do we need the condition when L is semi-positive definite?
So great question. So that's here. So just to think in the scalar case, right? So A is x plus iy. So what is shown here, this beta is the beta here, and goes from 1 to 0.99. You cannot reach 1. They are all exactly equal to e to the minus x. That's what you want. And on the left half of the real axis, and also elsewhere in the left half of the complex plane, it just goes pretty wild. So that's where it is used.
Yes.
Yeah, thanks for the very nice and clear talk. I might have a super naive question. So how does this method compare to just doing a Stein spring dilation?
The question is how to do Stein spring dilation for solving linear system equations. Right?
So it's about a complexity of, or
I mean, Stein spring, is not an algorithm. It's an idea. You have how to implement that Stein spring. I think that's the question.
Okay.
Yeah. So previously, for a long time, linear system approach is the only way people know how to dilate.
Mm-hmm. Okay. Thanks.
Any other questions? Okay, if not, let's thank the speaker again.